In this video, we're going to look at the terrain analysis processes in RAMP. So I'll go here. You'll see that there are a number of different methods in the terrain analysis processor in RAMP. Simple things like slope calculation, hillshade, rugosity calculations, topographic position index, standard deviation of elevation, slope variability. We intend to keep adding more and more different methods to this processor over time, so check back for different methods in the future. So let's just go through and look at what some of these methods do. Firstly, I'm going to mention that I have my favorite terrain data set up here that shows the mound with these interesting pockmarks, and we're going to look at what these different processing methods do to that particular input image. So the first one is slope direction. It expects an input raster, and I have a series of different options for what direction I apply my slope to. So the slope will be calculated in either degrees or gradients, and it uses a 3x3 kernel about a central position to look at what the slopes are in either of these directions. So I can choose to look at the slope to the north of my current position, or the north of the current cell that's being processed, or any other of the cardinal directions around that. I can also specify that I want to look at what the maximum slope is in any direction from the central cell or from the given cell that's being processed. And similarly, I can take the mean and the minimum. So maximum is quite useful, and it's the default option. So that gives you maximum slope, either downhill slopes or uphill slopes, doesn't matter. So let's just see what that does. We're going to take maximum, we're going to render it. So there you go. That shows me the high values are where I have my highest slope values, and obviously the green and the bluey values I have the flattest terrain. Let's look at the next one. This is another slope method that uses the 4 nearest neighbors. Let's skip over this one and look at the third order finite difference. The only difference between these two things is the algorithm that's used for calculating the slope. So we'll use third order finite. That's a very common slope calculation algorithm. And in the options now, we get to choose whether we want to output slope, which is rise over run, or gradient, or aspect, in fact, as well. Sorry, I believe slope is in degrees, my mistake. So let's look at, firstly, the slope map. The slope and the gradient map should look exactly the same. It's just a different measure of the angle. There's my slope map. Pretty typical looking slope map. So sometimes we refer to slope as the first differential of the seabed. That's another terminology that you might hear for slopes. Let's run the same again, but this time let's calculate the aspect. So here's my aspect raster. So as you know, you'll see that the values for aspect are 0 to 360 degrees. So aspect is the direction that the slope faces towards. So that's quite useful when you're thinking about site selection. It's often used for, say, solar panel selection, this sort of thing. So what direction is the slope facing towards is what aspect is. All right, let's move to the next. Whoops, wrong one. Let's go to terrain analysis. Okay, hillshade. This is a fairly popular thing to do to terrain data. Let's generate a hillshade. And we're probably going to have to do some work to render this in a hillshade friendly way. So let's take a grayscale color palette. I'm going to invert it. Okay, and there you go. That's a hill shading of my original terrain data set. Very useful, again, for intuitively looking at what the terrain looks like. It's often very useful to have a hill shade to help you visualize the terrain. Moving along, let's look at rugosity. So we talked about slope being the first differential of the seabed, essentially, or the seabed, or the terrain, I should say. And so slope is essentially the rate of change of elevation or depth. Rugosity is actually the second derivative. So it is the rate of change of the rate of change of the terrain elevations. And that's often referred to as rugosity. It's an approximation of how rugged or how rapidly the terrain is changing over a certain area. So let's look at the rugosity of this terrain data set. And I'll render it. And there you go. So unsurprisingly, those pockmark areas are the most rugose because they go upwards a little bit and downwards a little bit into the pockmark and then rapidly come back out again. So no surprise there that the higher values are associated with the pockmark fields that will have a more rugose terrain. Let's look at topographic position index, and we'll choose a kernel size of 9. Here we go. So what is topographic position index? Well, it's an algorithm that generally describes the position of the terrain, and it's often used to classify terrain. I thought I'd better get a definition of topographic position index for you guys. So it's used to measure the position of a slope, and it's used generally to classify upper slopes, mid slopes, and lower slopes, and it's increasingly becoming used to automate landform classifications. So if you want to understand topographic position index a little bit more, I would go and read up about it on the web. So let's move on and look at the next processor. I have standard deviation of elevation. Let's see what that looks like. Again, I'm going to use a kernel of 9 in this one. So essentially all this is doing is calculating the standard deviations within the 9x9 kernel of the elevation values within the original terrain model. So that can be useful for, again, it's kind of a measure of rugosity in a way. The last one is slope variability. So again, this is another rugosity type indicator. Let's run it. And let's render it. And what this one is doing is highlighting how variable the slope values are within the 9x9 kernel. And you get a very sort of pixelated result in this case, but again, you can see, unsurprisingly, that it's really started to highlight the pockmark fields in the image as having the highest variability in slope values across that 9x9 kernel. So that's a quick introduction to the terrain analysis methods that are available in RAMP, and as I mentioned before, there will be more to come, and we'll keep adding methods to the processor over time. I hope this video has been of help to you.